CAM pipeline. And thank you, Nicole, for recording. So take it away, Frank.
Well, yeah, let's have a discussion. I'm talking about pipelines primarily. I want to start by recognizing some of the people in the past. I've been doing pipelines at MSO for over 20 years now. It's scary to realize that. These are the people who've been involved. Some of them are managers, scientific consultant, but it was mostly been a small team. And I want to give a shout out to Francesco Federici. He had quite a lot to do with what I'm going to talk about initially. But just I want to say there's been a handful of people in my career that have impressed me as software developers. One was Doug Tody, but the other was Francesco. And when he was on our group, I've been leading these groups for most of the time. I went away on vacation for a few days and I came back and Francesco said, I have something to show you. And just a few days, he had implemented this NOIRLab high performance pipeline system. And just amazing. And we've been using it ever since. I also want to mention something about talking about science data pipelines, because I think we need a forum that's probably a little bigger than just the suites. And in history, we had pipeline workshops from 2010 to 2012. They ended because the next organizer didn't get around to organizing, which is too bad. But people from Space Telescope, NOAO, LSST, a number of people, some groups I may have forgotten, got together 3 years and talked about what we were doing, shared experiences. I thought it was a good thing. Too bad it ended, but maybe it's time for something like that within NOIRLab or even broader in the community like the SDPs were. I'm going to say a little bit more about that later. So the pipeline applications, I've been involved in pipelines now, as I said, for quite a while, and I just made a list of them. I'm going to use yellow to highlight things. So with NHPPS, the pipeline framework that I use, all of these pipelines, which means mosaics at Kitt Peak and Cerro Tololo. New Firm also was at both mountaintops. I'm going to be working on 2 in the next year. Another mosaic pipeline to reprocess this data we're pulling off the Save the Bits tapes that never made it into spinning disk early on. And then New Firm is going to go back to Chile and do that. I also want to point out this New Firm QR. There was some experience with having a mountain quick reduce pipeline at the telescope for New Firm, which is an infrared camera. It's quite important to analyze your data as you go along because it's very hard to see your science signal in infrared data. And then the big pipeline now is the DECAM community pipeline. I also want to point out that we've had collaborations. One was with WIN and NOAO in Indiana for the ODI, 1 degree imager. That did not end well. I could talk about it at some time privately, but we did have a couple of years where we worked hard to try and make such a collaboration actually work. I do have experience with Condor. The first pipeline that came for DECAM, it was a requirement for DES to have the dedicated time on the Blanco. And but they delivered, used Condor as the execution framework. I found it to be inefficient, caused problems, and then refactored it into these NHPPS pipelines. I also want to say that pipelines span a broad range of scale, from an LSST size scale to individual work that people do on their laptops and desk computers. And one can argue that end-to-end scripts that take raw data and produce some kind of final data product are a form of pipelines. In IRAF, we had CCD proc, which thousands of people have used. There's these do tasks, do fibers, do a shell. Gemini, some of the Gemini script tasks are of that flavor. They're complicated tasks, lots of parameters, but they take you from the raw data to something that you can recognize as your science product. And I'd want to say literally, millions of exposures. I mean, DECAM has taken over 1 million exposures, have been processed and archived by these pipelines. In thinking about the vision or the view of how pipelines work, there's actually 2 main pieces, and I just want to highlight the components in a pipeline. There's some processing environment, and that can range from your computer to the cloud. The highlighted one is that the pipelines that we've been working on with DECAM and recently use a dedicated cluster. One of the things I've learned over the 20 years, we've done things, didn't know, we call them something, and then later on the buzzwords come along, and then people say, oh, we're so great, we have service-oriented architecture. And then I say, oh, now I understand what term you want to use. And the one I learned in the last week from ADAS was the term on-premises. So what we have is an on-premises cluster that processes the DECAM data, the mosaic data that we took for the legacy survey. Then you also need a file system of some kind. They fall into local and shared. Some of the pipelines I've worked on use local disk and then networking to share results. Now we use a shared file system, which makes development easier, but then you have a stronger dependence on your shared file system. You usually need a database in order to keep track of the processing states or the calibrations or whatever you use a database for. We use Postgres here in Tucson. You need a source and sink for your processing. It can come from disk or an archive. The pipelines I work on now are, we pull the data out of the archive after they come from the telescope into an archive. We pull it out, process it, put it back in an archive. But everything can work perfectly fine by first staging it on disk. And then usually what people think of as one of the biggest pieces, the execution orchestrator, the thing that runs the individual pieces of the pipeline and keeps track of the data sets that are being processed. Some examples are that I'll talk about NHPPS, but then there's Condor. There was a TerraGrid system called OGCE that I worked with. LSST has theirs. Right now I can't think of what the name for their execution orchestrator is. But I want to make the point that the applications are separate. Every application, while you call it like the Mosaic pipeline or the Newfern pipeline, it's really the application you're talking about. That is less general, that's specific to whatever data set you're doing, and they can have different structures. In the community pipelines that I work on now, the structures is data parallel. That's pretty obvious for astronomy and for imaging systems, at least, that our data is always very data parallel. You can process different exposures in parallel. The logic I ended up using for most of the pipelines I learned was called scatter gather, which means you take a big data set, break it up into pieces, hand that out. Each of those might break up into more pieces. And then when each of the individual little pieces are done, they get passed back up the chain. And in the end, you have your final product. Also, pipelines I'm talking about are coarse grain, which means that the chunks that are being done, the basic modules that do most of the work do a lot of work as one process. And then it's file-based. That usually goes along with coarse grain. That one big step finishes, passes its results to the next step in files. The other aspect of an application is what your choice is for programming shells, compile tasks, libraries, toolkits. As you'll see, I use IRAF heavily as my toolkit. The language is how you handle parameters. So the NHPPS originally, we have not been very clever with acronyms and names. So when Francesco first presented the software that I'm talking about, we had no name. I said the NOAO high performance pipeline system, high performance because it works on a large cluster of machines. Now I can change the N to NOIRLab, but originally the N was NOAO. So what is NHPPS? Well, it's a conceptual descendant of Opus. So this is an example that we actually did adopt something from some other project. Opus was the execution framework for Hubble initially. And NHPPS adopted the logical framework concepts of that, which I will get into. So NHPPS is very lightweight Python code. Francesco was an expert at Python. And then because it's distributed, the different Python modules talk to each other with remote objects, which is a system called Pyro. NHPPS will execute any host command. Normally they're in scripts in various shells, IRAF shells, C shells, Python shells. And what it does is it passes the environment information from the execution and parameters that have to do with the environment, not the application itself, but the environment and system parameters. So with NHPPS, when anything starts up, it's told what the last process was, what the state of the blackboard, which I'll talk about in a second. The thing that makes it a kind of pipeline that you might be interested in is that it's event-driven. It supports many different kinds of events, but the two that are almost 100% used are file triggers, where a file appears in a directory. NHPPS is monitoring it. Something happens, that's an event, then something gets executed. And the other is a blackboard, meaning keeping track of the status flags of all of the processes that have run before, whether they succeeded, whether they failed, whether they haven't run yet. What's great about an event-driven system is when you design the data flow, the workflow, you don't really need to think about what has happened in the past. You just say this process will only run when this file trigger appears or where this blackboard status flag changes to something that says I can proceed. And that allows parallel processing. So if two different stages can run, given the same trigger, they can run in parallel. So I think that if you take something away, that's what NHPPS is. It's an event-driven system. The blackboard is a component within NHPPS that the operator ends up spending a lot of time controlling. So it's very, very nice, because if the blackboard shows that something fails, normally you just have to find out why it failed, fix it, then change the blackboard, erase it, and say, okay, go again. You don't have to start over. It's very modular in that sense. And there are tools that the operator uses to manipulate the blackboard. It's distributed and service-oriented. So the structure is that it's called a directory server. It just means a server that's keeping track of all of the hosts that are running components of the pipeline framework. Then there's node managers. Every computer has various names: a host, a node, a computer. There's one node manager on a host that keeps track of everything that has to do with NHPPS on that node. Within the node, there are pipeline managers, and I'll say a pipeline, and I wish I could find a better term, that it's like sub-pipelines, the overall pipeline, and then there are pieces that are also aggregates of many steps that you put together, and those run on all the machines that you want them to run on, and the pipeline managers are the one that do that. This allows you to have some hosts doing some steps and not others, for a machine to go away, come back, to add one. It's all based on these pipelines, which are the services that the overall workflow can say, I want you to do some work on this piece of data. I also noted a command that's used, pipe select. What's nice is that there's one simple command that does all of the load balancing, distributing. So the pipeline, one pipeline will say, I want a service, this service, tell me which machines have it, and based on how its load is and so on. So it can be further optimized to balance loads, to tell you which machine to be used next, which service. And then the last aspect is the pipeline description language. Somehow you have to define how the workflow is broken down. NHPPS uses XML, which was the big thing at the time and still is a very useful way of describing things. A point I want to make is that the core NHPPS does not impose much on the pipeline application. It's a very small thing, and most of what I'm going to talk about next are conventions and layers that are put on that to simplify use for the particular application. So the application layer, you decide what your strategy is for these events and how you're going to identify them. So there's Blackboard flags. There's C would be completed, P is processing, W is waiting for return of a service, H is halting, fatal errors, recoverable errors. That's the logic that decided on. And then how the file triggers are going to be used within the pipelines I'm working on. They're almost exclusively used for triggering a service. The beginning of one of these sub-pipelines starts when a file appears containing data to be processed. The scatter-gather strategy requires steps to say, okay, I want to call a CCD proc pipeline, or I want to call a stacking pipeline, and I'm giving you 30 different things that I want. I'll wait for you to return those 30 some pieces so I can go on to the next step. And then again, these sub pipelines, which are the services in this service-oriented event-driven system. We also have a data set strategy, which is very important. Because of the scatter-gather, we start with some data set name, and a data set is any collection of exposures to be processed. So for DECCAM, it might be a night. I'll get to that in a second. And organizing working directories. So everything's oriented around data sets. And then the shells, one of the things that was added that's heavily used is an IRAF host shell. And the point of this, making it a layer, an application layer, as opposed to in every single host, is that there's so many startup steps, defining parameters, loading packages, setting defaults, writing out initial log information, preparing the log files. That's all done so that the application programmer, wants to do a state, simply says #bang pipecl, and then starts directly into the actual component, the processing that's of interest, not worrying about setting up a whole lot of stuff. I think it works really well. The scatter gather parallelization, as I already alluded to, you start with a data set, which is any collection. You can give it any name you like, but typically it would be a night of data for DECAM or, well, DECAM, say, or Mosaic. It might be a run, which is important for something like new firm, where you need to deal with various things that propagate through the run. It can be by a project. That's become more common. Somebody will ask, I've taken 10 runs scattered over 2 years. I have these data sets. Can you put them all together, process them as a unit, make stacks? So that's at the top level. That's just passed on to NHPPS as a file trigger. And there's a higher level command to say, pull out of the archive all these files. And then the top level will start up. It'll break it up by filter, can break it up by other things. So each filter runs in parallel, and then that can be broken up by the calibrations, by CCD. And what I want to point out is that in the process of this scatter gather, the breaking up into pieces can take different forms. So for CCD, they're broken up by CCD in a mosaic. DECAM has 60 active CCDs. For the CCD proc step, applying biases, dome flats, it's broken up by all exposures, all CCDs at one, all exposures from one CCDs. That allows the calibration files to be cached and be very efficient. The more common thing is to break it up by exposure. After you've done that, I want to do all these CCDs from that exposure in parallel, because I want to tie together the different sky levels. Dark sky stacks, that's would say, give me all the data from that filter. I want to make a dark sky stack. And pointing stacks is a different kind of grouping. Look at all of the exposures you have at this point, find all of the ones that are at the same pointing, so you can make a stack. And that happens automatically in these pipelines. The observer doesn't have to tell you in advance what things go together. The logic tries to do that.
Before you move on, Frank,
yes.
Can you go back? I think Robert has a question about how it handles sporadic failures. Do you want to ask that, Robert? Instead of
sure, yeah. Can you hear me?
Yes.
Yes, can you hear me? Hi, Frank, this is Robert. I was wondering, I know a little bit about, very little bit about like several popular workflow managers like SnakeMake is, for instance, one which works like Make, in that it compiles a directed acyclic graph, I think it's called DAG, from some workload description. And one benefit is that when you run it on 1 million files and 2 files fail, when you run it a second time, it only runs on those failed files. So I was wondering how NHPPS handles, sporadic failures at some task level.
So yes, that's where this Blackboard comes in. The operator can have a view of the Blackboard. It can be broken up in different ways. If a piece fails, then a flag will appear on the Blackboard. All the other parallel stuff continues running, all the other exposures. But say one exposure, one that I've encountered recently because our archive had some corruption problems, is one of the early stages, the file is corrupted and it fails. I can just say, fix those and move on with that. So it's part of the scatter gather, however it was broken up, that one parallel piece will stop and the operator will find out based on this flag. And like I said, they can fix it and restart it by simply setting the flag back to you're ready to go again.
And so it doesn't have to repeat the previous steps before it failed.
Right.
Okay.
Sometimes if something really bad has happened, all the exposures were taken with a missing CCD and you didn't know about it, you might have to go back a service to say, okay, all the basic CCD processing was correct, but now your handling of the sky is all messed up because of this missing one. So you can also go back in terms of the different higher level pieces, or you can go back to the start once you fix it. But the important thing is to be able to catch that. And the default for what NHPPS does, it executes a host command, looks at the return status. The person who programs that host task has a convention for what the return statuses can be. And it could be halt or error. But if nothing else happens, if the thing just crashes without being caught, then NHPPS will pick that up, you know, a status flag of 1, and pass that on and say failed. Usually that would be the fatal error, but those can often be fixed. So that's how it works, is that only the piece that's running, only the module that's running will fail. The operator finds out, can fix it. Everything else will be running to the end. And then with time, you catch all of these things, and the pipeline now, the DECAMP pipeline, virtually never fails on anything.
It's been
just nice.
Yeah. Thanks. Appreciate it.
But you did say the acyclic graph approach. So how do you describe a pipeline? There are different ways. And I really like the way NHPPS does it and I coined the term pipeline description language. You can call it whatever you like, but there has to be a way to describe a pipeline. And this is just an example of the current state of one of the sub pieces is the CCD pipeline. Basically, all it does is do the dome flat, the non-linearity, a bunch of basic steps. And this is the file that actually describes it. That's what I put together. There's a start command. There's the thing to see is that this is initially you have to do the entire XML. I'm going to show that in a second. But in the next generation, I extracted it so that there's a compiler component, and only the key things appear here. So this one says the CCD proc step will start when the start step has flag is P. CCD amp will start when the CCD proc step says C, completed successfully. The done step will start when CCD amp is done. You don't need to know this, other than people might think, well, programming in NHPPS with XML, I don't like XML, it's complicated or not complicated, depending on your point of view. It is extremely simple to, I could put together one of these in minutes when I want to do something special in a pipeline. It gets expanded, and this gives you more example of this event-driven architecture. So that one step, module name CCD proc, and when it should execute, gets expanded into this, and it's only a piece of it. So there are trigger conditions. In this case, it's saying when CCD starts flag, Blackboard flag is P, and when its own flag is _, which is the convention for saying, I haven't run yet. I will run whenever the conditions are right. So the XML sets out what the triggers are, what the event is. There are some general things like, if you run for 8 hours, send back a status flag of timeout. That's the kind of failure that's a little harder to catch, but NHPPS will catch it. Then after the trigger conditions are met, there's a pre-proc action, which says what to do when that happens. In this case, all it says is set my Blackboard flag to P, tell everybody else I'm processing, don't let anybody else run me. Then there's the processing action, which can be a built-in task in the Python, but most of the times it's just an external task that's found by the normal Unix way of finding things. In this case, run the command CCD proc. Then there are post-proc actions, and this is where all those error conditions that were mentioned come from. So there can be any number of these blocks of post-proc action. I only show one. If the exit code value was error, set my Blackboard flag to E for the operator to find, and that stops that particular data set from going further. Then there are one exit post-proc actions for success, for what to do if there's no data. That's another condition you have to catch, and so on. And so that's the full description of that one step. So the pipeline definition language is this XML. I think it's particularly nice, but that's the way. It's not the acyclic graphs, which I dealt with the supercomputer OGCE, which had a different one. The Blackboard, historically, we've spent time when I had a team of people, small team, 2 or 3 people, trying to come up with some fancy GUI-oriented Blackboard monitor. But I've learned over the years, keep it simple. So the Blackboard monitor simply refreshes an X term every time something changes. I've highlighted in yellow the various things to give you sort of a feeling for how this thing works. This is not showing all of the steps. These W's mean that a sub pipeline is running. In this case, it's taken 12 pieces and farmed them out to run 12 exposures in parallel. And now this higher level pipeline, the FIL pipeline, which is the filter level, there's a process ID, so that every data set that runs gets a new process ID. So you can rerun something and you won't clobber the data you've already done. And it also shows how the data set conventions build on themselves. So this Odin one, it's processing a narrowband filter. It wants to make a stack of all that data. So a sub piece just gets tacked onto the data set name. And now when I took this snapshot, it's processing, making a stack of everything that was done at that particular pointing. So like I said, this is when I'm running the pipeline, mostly I have a little window up showing me this, and periodically I'll look at it. Are there any failure flags? Most of the time there aren't. I can quickly look at this and tell what has happened. And I added something so that another failure mode is you run out of disk space. DECAM uses a lot of disk space. And it's very annoying when you run out of disk space, because that you can recover, but it's a lot of work to recover because all the files are left in bad states. Okay, that's my presentation. I was trying to go fast. I debated whether to make these comments, but I was wondering when I had volunteered to do this, what really is the purpose here? What can I convey? Maybe I shouldn't give a talk because I don't think anybody's going to adopt NHPPS, but I put together these comments, which could be food for discussion. First of all, I think that NHPPS and this on-premise systems are great for NOIRLab scale data, even DECAM with its gigabytes of data all the time. I want to make a comment about this on-premises. I've had experience with 4 different supercomputer centers where groups will say, well, we'll run our pipelines on the Indiana or NCSA or Berkeley. And oh, we're great, they run really fast, we share it with everybody. But my experience has been there's so many headaches. File systems stop working, machines go offline for upgrades. Our on-premises system for DECAM and NewFirm and the ones we've done, I basically control them. They rarely ever fail. You know, we can go 6 months with no failure, just processing data merrily along. If something is not working right, I can take a machine offline and pass it on to the systems people to figure it out. So anyway, I really one reason I gave this talk is that I love this system and I've had a lot of experience with other systems. So take that for whatever you want to take it for. I think that the NHPPS pipelines will remain at MSO for at least a few years. DECCAM, New Firm, any other ones. And partly because you should realize that right now, for the last 8 years or so, basically, I've been a group of one doing the pipeline work for MSO. And so obviously I use what I'm comfortable with. And when I'm going to develop the New Firm pipeline, we had an older New Firm pipeline, use that. It was also an NHPPS. But beyond that, the handwriting on the wall, to me, is there's not going to be any uptake within NHPPS. I should say that I did try and publicize it through the science data pipeline meetings we had, and it was used by Space Telescope for their legacy reprocessing. So NHPPS has been used outside of what was NOAO, but I don't really expect it. But I think I want you all to hear that I think this is a good system. There are a few people in CSDC that are working on DECCAM calibrations with LSST. I think it's on an Antares effort. How that's going to turn into production, I don't know, but that's, I think, where it's going to go. And that might be a reason for there to be a NOIRLab or a CSDC data pipeline meeting, so we can actually talk to each other. I didn't really find out too much about what was going on with this LSST work until somebody was asking me questions about how DECCAM actually needs to be calibrated. I think my prognostication is there will eventually be a transition to the LSST framework for pipelines. The difference is thousands of people hours have gone into that. As I noted, the first data processing pipeline groups was 2010. LSST was even then having a dozen people working on pipelines type stuff. So they put a lot of effort into it. They're the 100-pound gorilla. Yes, it probably will be due. Well, I think there will be a transition to the cloud, whether we take our NHPPS pipelines to the cloud or something else. It could also be handed off to a supercomputer center, though I hope not from my experience. DES did offer to take over the DECCAM processing, but we talked about it, didn't seem like a good idea. And finally, one of the things I think will be lost will be being responsive to community-friendly features. One of the things of being a group of one is that when a PI, a team says, I'd like my data processed in this way, which is not the standard way, they can talk to me. I can make the changes. I can make it happen. I'm part of their team. It works out great. Probably the same thing happens with people that use the DES pipeline. But that's one thing I would worry, that is, as you go to a bigger group, have an LSST pipeline doing DECCAM, whether it'll be quite as responsive to people. I could stop here. I could talk briefly about my asteroid work. What do you think, Joanna?
Well, let's see if people have any questions, or you had lots of good comments and prognostications. Let's see if people want to talk about those a little bit. And it seems like Robert has his hand up.
As long as nobody else is raising their hand, maybe I can
No.
start off. Yeah, thanks. Maybe I can start off. Frank, to the point that you're making here, that the LSST framework being the 100-pound gorilla, and that you think that there will be no uptake of NHPPS elsewhere, including in NOIRLab. I was wondering if you would agree that part of this is maybe that some of the steps of the tasks still critically depend on IRF being available, and that is not being supported since many years already. There are efforts, of course, to keep it alive a little bit longer until viable alternatives are available. But I was wondering if you think this is part of the issue with frameworks that still depend on IRF.
Okay, so there's 2 points that in response to that. First of all, the reason I call this an NHPPS presentation is because NHPPS is not IRF. It is purely Python. It is small. I did spend time trying to package it into an exportable system. It was exportable. So IRAF does not enter into the framework. Now, what I said is that I then put layers that made using IRAF in that very simple by adding this pipecl shell. The dependence on IRAF, unfortunately, management managed to convey a message that IRAF wasn't supported, which is not true. We do have people that support IRAF. I certainly support it with people asking questions. It is vitally dependent. If IRAF were to go away tomorrow, DECCAM pipeline would go away. So it can't be. Now, it may not be as widely used in the community, though it's actually widely used overseas primarily. So IRAF is not going away. The support level depends on our management. There are talks about moving it into the next generation of computers. But yes, you're completely right that the DECCAM pipeline, the NOIRLab pipeline, all the pipelines that I said, because I wrote them, are heavily dependent on the IRAF toolkit. But it's been that way for 20 years. It's still going strong. If something needs to be changed, I can change it. It does have the effect that it's harder to bring somebody in, but because when we had Rob Swatters doing the NOIRLab pipeline, he wrote some of the modules in Python. They go in fine with NHPPS. So it's not such a big thing. I think the question you're addressing more that makes it harder to propagate it further is the question of support. When you have one person, it's really hard to say, can I adopt this? Then I have to teach people how to use it. And something like LSST, hopefully they will invest in supporting other people to use it. I mean, they advertise, use the LSST framework, but I wonder how well they can do that once if MSO adopts it for something, or NOIRLab adopts it for something and they have problems, go to the LSST developers, say, well, right now we're just starting to be flooded by gazillions of exposures from LSST. Can we really turn around and fix the fact that the CCD proc doesn't work the way you expect it for your kind of data? So that's a concern, and that's where it makes it hard, is the support and exportable nature really requires more people than management normally allocates for that purpose. And unlike a business where that's your data product, you of course want to support your clients. I hope that answers some of your question.
It does, and I share your concern. An army of one, like in your case, you have the difficulty of getting somebody new on board and help out. But an army of 1,000, like at LSST, I think they suffer from the inverse problem, and that is that there will be no customizations available. There will be one agreed upon way of doing things. If somebody wants a special processing, good luck. Now, some observatories like ALMA had published the CASA software where you can go and re-reduce your data yourself, including recipes that they provide. And that's hundreds of gigabytes of data we're talking for each program. Now with SST, this would be even more. So I don't think anybody would be doing that. And I think also reprocessing all the SST images, that it's only planned on the 10% level for institutions, big institutions, not for individual users. Thank you.
Thanks. I think Mark has a question or a comment.
Hey, Frank, that was really nice. Thank you. Takes me back. You mentioned the example of STSCI using NHPPS for a reprocessing effort. Did they do that for? Do you remember? Was that done for like all HST data with all instruments, or was that only for the imaging data?
Trying to remember, this was years back. No, it was for a sub thing. It was like reprocessing the valuable legacy components. So it was a subset of data that they wanted to reprocess, and it was a small group. So maybe 10% HST
Oh,
data.
okay.
I can't remember the name of the program. It had its own name,
And it
apart
may have
from,
been, and it may have been a particular instrument like, ACS or something like that, or, or a small number of the instruments. The reason for my question is actually, most of the examples that you've described and that NHPPS has been used at NOAO for are, wide field imagers, and the problems you discussed are ones in which, you have things like DECAM that have lots of detectors, and so there's a lot of opportunity to parallelize and so on. Other kind of application for pipelines that we might be thinking about in the future, like for example, we're well in the future still for things like TMT and GMT, but we are talking about routine pipeline processing for data from those telescopes. Those are more like Gemini in the sense that they are, narrow field telescopes that have a variety of complex instruments with many different modes that will be used in many different ways, as opposed to a wide field imager that kind of, produces a lot of data and a lot of CCDs, but is kind of doing the same thing most of the time. And I'm just wondering whether or not you see different challenges if, very few places on the ground have done routine pipeline processing for the example I was describing, where you have a bunch of different instruments. Some of them are spectrographs, some of them are imagers, some of them are integral field spectrometers or something like that, and they're all doing different kinds of things. So they each need a different pipeline. But would you see a framework like this is still flexible enough that it could be used in that kind of a situation?
Yes, that's what I was trying to get across, that NHPPS by itself, the Python part imposes very little on the pipeline application. So it's like Unix or something. If you want something that will trigger a host command based on some condition, files appearing, and then you want to monitor it as it goes along, you can apply it. The layers you put on that to build an application, it's your choice. So I think by itself, it's so top level that it can be used for something like that. Most of the effort for your team of programmers will be in the application itself, and whether a spectroscopic instrument can benefit in some way by the high performance part of it, the ability to trigger things on different hosts, or organize things in different packages, the sub pipelines. That's a design. So most of the effort has to go into the design of the application. It's the same concept that about like Condor. Condor is the same basic thing. If you want to execute something on a cluster, you need something that will do that for you, and you don't have to think about it. That's where I see NHPPS. It could be used. Whether it would be, I have built spectroscopic pipelines, but I did that with scripts under IRAF.
Mm-hmm.
If I was still young and was asked to, I would love to do a spectroscopic pipeline, but I really don't know what the problems would be encountered by it.
Well, something like DESI, for example, is not so different in the sense that that's, again, a massively multiplexed thing, and there's zillions of spectrographs and zillions of detectors, and they're all doing the same thing all the time. So it's easy to imagine this same kind of framework used for that. The orchestration maybe for something where you've got, you're trying to routinely process a data stream from a telescope that has a whole bunch of different instruments, maybe, using different instruments in the same night and for different kinds of programs and something like that. There's more bookkeeping involved in all that. But in terms of the job execution, the framework should be okay.
Yeah, and this thing gives you an idea that when the legacy survey processing was going on, we were simultaneously doing DECAM, the Mosaic 3 camera, and the 90 prime camera from the University of Arizona. They were all using the same NHPPS. We just try to adjust our host loads to not clobber on each other, but they all ran in parallel. And the other advantage for something like that, for an institution like ours, is that if you have multiple instruments, it really is pretty important to have the same framework, so you don't have to train all these different people. This processing I talked about, we had David Herrera in our organization who was running the 90 prime and the mosaic processing, but he could also run DECAM because they all follow the same high level. They had the same kind of blackboard view. It fails and recovering from failures were the same. Getting data in and out of the archive was the same. So if you want to do multiple instruments, try and have as much commonality at the orchestration level as you can. Then the applications, of course, will be different. And there you might have experts in each one.
Yep. Great, thank you.
Thanks, that's a great question, Mark. And I'll just second Frank's idea that you want to have something that everybody knows how to use. It makes it much easier. I actually had a question. I don't see anybody else's hand, so I'm going to take.
Yeah, there's a question in the chat, Joe.
Oh, I do see it. Thank you. But I have a related question. Before we go to Stephen's question. And so when you talk about, the idea that having a common framework so that people can use it more easily, I understand that this is a pipeline that's only used within NOIRLab, and if users have a question or they want to do something different, they ask you and you do it. Is there any thought that this would be something that users could use themselves? Is that not either by like using it on our facility, in our facilities, or using it in their own, or maybe that's not realistic. I don't know. Anyway, I was wondering about that.
Yeah, well, that is one of the most common questions with any pipelines team is, okay, you've written this nice pipeline for JWST. Can I use it locally? And then like in response to Robert, how much effort does it take for you to do that? The comment I would make, I get that question occasionally. Can I run the DECAM pipeline on my supercomputer in Chile? That came up. And the problem is that if something is good enough, it's going to be complex to some level. And this stuff is complex enough. And it's designed for on-premises cluster. That's one of the things we had to go around with the Indiana ODI stuff, was how could you run this on your supercomputer when each node has to know about the names, the addresses of all the other nodes that are participating. So the complexity and being a team of one, people also barf on the idea of IRAF, but IRAF is easy to install. NHPPS is easy to install. Learning how everything works, how you start it, how you manage it, that can take a while. I've had people that I've trained to use our pipelines here, like the New Firm pipeline, and it takes months to learn the conventions and this step is doing this, that step is doing persistence, and that's my difficulty. What has happened is that somebody says, I want to run the DECAM pipeline on my supercomputer. I say, well, here's the code. We're a national organization. Here's the code. But really what you need to do is learn all of these steps that are done, the algorithms, how nonlinearity behaves in DECAM, and implement it yourself. And a lot of the steps are not complicated. Subtracting a bias, applying a dome flat, all those kinds of things. So that's where it has gone, partly because of as I said, the manpower of one. But it's also a way for somebody to learn. So when somebody said, I want to use the LSST pipeline, I heard it's easy. I got a sample pipeline. Oh, but did you do the nonlinearity correction? Oh no, how do I do that? Then I can give them my document of how it does, what the calibration file looks like. that is a better way to propagate some of this. But again, to answer your question, pipeline is complicated enough that it's not the most trivial thing that people think, even when they say, I have a whole department here at NERSC in Berkeley that's designed to port somebody's software. Yeah, I can give you the software, but you're going to be asking me questions immediately. What is PipeCL, or what is a task here? So no, it has not worked that way. What we tried to do with ODI was to have a collaborator, Rob Swatters, develop it, work with the people in Indiana, and it ultimately failed because their supercomputer just would not work right. And they wanted to go off and write their own Python thing. So there are many challenges. It's not as easy as people say. You can't share software that easily. But
Okay.
if you have a team that can concentrate on making it exportable from the beginning, like IRAF, then it can reap benefits. Yes, I agree with that.
Great. And Stephen, are you online? Do you want to ask your question, or do you want me to read it?
Hi. Well, my question is kind of open-ended, and I think since we're at the end of the hour, maybe we should pass on it. Very briefly, I was just going to say to Frank, okay, I think you've presented a really compelling motivation here for your design. If I were going out shopping for a pipeline strategy at other major observatories, would I find things that differed mainly in detail and implementation, or would I find things that were totally different in philosophy and have big choices to make?
I think it's somewhere in between. And because they have slightly different niches, so you might immediately hit Condor. Condor has its features that are good and not so good. You want to run it on a supercomputer, well, then you have to learn their queue system and so on. So some of the logic is the same. The pipeline definition language, that can differ quite a bit, like LSST, because theirs is more in-memory type of thing. So I'm not sure you can go out and shop and find exactly what you need. More, you have to say the scale of my work is, I'm a small group. I need something. NHPPS would fill that bill better, or Condor, or I'm going to be doing huge LSST reprocessing in my own institution. Then you'd be using the LSST framework. Yeah, you're right. This is a philosophical question that's hard to answer.
Thanks.
And since we're just about at the top of the hour, I'll thank Frank for sharing his experience. It was fantastic. Thank you very much. And I want to just say that there was a question in the RSS Slack channel about what's happening, the future of suites, where to find the schedule and all of that. And I will say we have talks scheduled through February, skipping January because of AAS. And I will put the schedule in the Slack channel, and posting it somewhere on the NOIRLab intranet is a great idea. So I will look into getting it there as well. And pretty soon, since we're covered through February, I don't feel like, we have to get more people to sign up right away, but it'll be coming for next year, as some of us talked about at the RSS meeting on Monday. So thank you, everyone, and thanks again, Frank. Much appreciated. Take care.
Thank you all. Bye-bye.